Your phone. Hello? Jonas, can you check whether or not you can hear me on Zoom? Hello? Hello? Okay, perfect. Okay, so we're recording. Welcome everybody to our second to last lecture. So it's gonna be the last lecture that will also generate some exercises, and then next week we're gonna have basically like a closeout lecture, and then I think we kind of end exactly with the last day of lectures. So there's not gonna be an exercise the following Monday, and so we'll use this to kind of give a bit of an outlook and maybe discuss the fusion models. Which will be like a nice end to this second part of this lecture, which was basically all about generative modeling. Okay, before we start, exam. As you've seen, so Jonas put together like a nice little table in order to kind of assign exam slots. So I've seen there have been quite a few people that signed up. So if you haven't signed up, make sure you sign up. But I guess whoever wants to do the exam already has seen this. Okay, so Jonas had an email for this. And then, so there's, as I said, okay, we have like one more week of lectures, and then there's a little bit of time before we have the exams. And so I'll be traveling a little bit, but I'll also be kind of in the area for a few weeks. And so if there's demand, we can also do like office hours. We can do like Q&A, review of some exercises. So if this is something that's interesting, we can try to schedule something either like on the usual exam slots, or for people that can't make the exam slots, we can be a little bit more dynamic and when we do it, because it's the lecture free period. Okay, so maybe just let us know over by email or Discord or something if that's something that'd be useful. Okay, yeah, okay, so then we'll try to schedule something at least within the weeks that I'm here. Okay, so back to machine learning. So we're continuing our saga on generative modeling. So this is our last week. So last week we kind of reviewed like our variational autoencoder, and so there was a little bit of discussion on kind of what is special about variational autoencoders. And yeah, we're gonna have a lecture on Friday, but it's gonna be kind of yeah, so there's no exercise on Monday. Yeah. Okay, so we had our variational autoencoder. We discussed a little bit what's special about it. The main point is that we're kind of trying to backpropagate through like a stochastic process, which is a priori not differentiable because it's discontinuous because you're sampling. And so there was like this entire idea about reparameterization of random sampling, where basically you're outsourcing the random part of what's inside of probability distribution. So there's always some randomness and some parameters that shift the randomness to the right place. And so the parameters that shift the randomness to the right place is something that the neural network predicts. And then it's just you need some kind of noise source. And so this is then kind of just rerouted to be like an input to the network. And then after the VIEs, we discussed kind of like a nice little thing that came up, early in the kind of advance of deep learning in the last 10 years, which is generative adversarial networks. It's a kind of game theoretic version of trying to sample, realistic looking data. And so you had like this game between two agents. So one is trying to generate images. There's another agent that is trying to differentiate between real images and these fake generated images. And so by kind of competing against each other and playing this minimax game, you find like an equilibrium, which is like the Nash equilibrium, and then you can get very, very highly realistic images. And so this was kind of the advance of kind of generative, what people sometimes call generative AI, and creating non-existing people and so on. And so before DALL-E and all these different things. So DALL-E can now generate all different things. You can generate faces and whatever you want because you just type it in. But this was kind of like a precursor and made it really look like very high fidelity images are possible. Okay, so then so just as a review, so let me just try to get this out of the way. So these are the generative models we discussed mostly so far in detail. As you'll see, we also discussed a different generative model actually a couple of lectures ago. But so we discussed the VAE on the left-hand side. So we're training the VAE as an autoencoder, where autoencoder is also a structure that just happens to exist kind of from like a data compression point of view. But with the variational autoencoder, you can basically chop off the encoder part. And then once you have it trained, you only use the generator part and you put a noise and then out comes some new data. And so this was the VAE. And then our GAN, we have like our generator, it gets some source, it transforms this random noise into some generated data. And then the GAN either looks at the generated image or the real image. And it basically for each of these images, it needs to discriminate or classify, is it a real image or not? Okay, great. So this is our baseline. And so we'll continue kind of in this direction, but something about the distribution of the data. So either we learn to generate new data that is similarly distributed as the data that we have. And so this is one direction of what a probability model can do. And then on the right-hand side, we have, okay, you can try to estimate the density directly and answer the question, okay, how likely is a specific sample? And there are also cases where you can try to learn to do both things at once. And so this is what we're gonna kind of discuss today. Okay, so why is this different? What we're going to do today from what, for example, the GAN is doing. So the GAN can completely ignore like this right-hand part of generative modeling or like unsupervised learning. We're not really interested. We're only interested in generating data. I don't really care how likely it is. I mostly care that this is kind of similarly distributed. The data that I get out of this machine is similarly distributed to the data that I have. So that's like a important piece. And so there's no piece in this entire architecture that tries to evaluate P of X. So for the okay. So what's the difficulty? So I mean, so that's nice, and so we've seen the have features that look very different. The discriminator will pick up, and so it's basically picking up differences in the distribution. But it's kind of an indirect way to do it, right? So you're not really comparing the density to the density, but you're comparing samples to samples, and so this is just difficult, and you can imagine independent of like the mathematical formulation why this is not the easiest thing to do. Okay, so in the VAE, we tried a little bit harder. And so here, actually, we're modeling to some extent like something that is, has some relation to the actual density. So we're comparing samples to density instead of samples to samples. And so the learning objective that we discussed here was the elbow. which is the evidence lower bound. And so it's not exactly P of X, so we cannot answer what P of X is, but at least we can lower bound it. So elbow is lower bound to this thing on the left. And so we decided, or we derived that it's kind of this expression, which is like an expectation value over the joint and the posterior. Okay, so now what we have is basically, okay, we can now and stable to train than like this minimax game that we have in a GAN. Okay, so now we have basically instead of comparing X to X, we compare X to P. Okay, the way what we had in the VAE is, as we said, okay, we're not really modeling P of X, but we modeled kind of the joint density, and in the joint density, we made a modeling choice where we're splitting the joint density into like the prior, which we fixed. So we wanted the prior to be like a standard normal Gaussian, so that once we want to kind of generate data, like in this picture, we want to know how epsilon is, or like the latent code is distributed. So that should be like a standard normal Gaussian. And so we fixed this part already. And then the only thing that we are really modeling with the neural network is kind of this conditional distribution P of X given. And so they're in generative modeling, they're models that try to do like a tractable likelihood. And if you have a tractable likelihood, because you have one point of indirection less, you have like a stable training and it's nice and you can, get somewhere quickly. But then, if you're actually trying to model P of X or, like a lower bound of P of X, then this is a much harder problem than just generating samples, because now you want to basically do both things at once. So you want to be able to sample from the thing, and you want to be able to evaluate P of X. And so like a density, if it's like a very peaky density, like the density is actually varies widely between 10 to the -7 and 100 and so on. Like there's like a very wide dynamic range, and so this is a complicated function to learn. It's not only a function, it also needs to be normalized, right? So that it integrates to one, so that it's a probability density. And so just learning density is typically just a hard problem in machine learning. And so we basically pay the price of like a more stable training by forcing ourselves to solve a harder problem. And so this is kind of like a trade-off that exists, and we've seen in GANs. So like the sharpness of the images that you see in GANs. And so one of the issues that we discovered was mode collapse. So basically the generator can figure out, okay, if I am able to generate like one realistic looking image, I will always fool the discriminator. But and I'm not really a generator. I'm only kind of picking out like one example. And so this is really not great. And so you have like a, yeah. Yeah, exactly. So you would see, for example, if you trained again. So did you actually train again? Yeah. So if you train again, you'll see like the digits are not evenly distributed, and so this is like a part of this mode collapse phenomenon. And then you can try to force it to have like a more diversity and so on. But kind of by default, like you're not mandating any type of diversity, and so that's the problem. Yeah. And so we'll like tend to do something that can generate easily, and like a one is like another complicated thing to generate. Okay, so basically, okay, we want to avoid this phenomenon. And so one of the ways to avoid it is to really say, okay, I want the distributions to be same. I don't want to only sample from the thing, but I want the distributions to be the same. And so you can say, okay, what do we need as a measure for distributions? We can use our forward KL divergence, which is the same thing that we use in kind of inference when we introduced it, right? And so basically forward KL divergence has this definition. You take the kind of what is actually happening. And so let's say you have all of these different samples, right? And so, okay, so a mode collapse means that your estimated distribution Q of phi given X is not covering all the samples, not the full diversity of the training data that you have. And so it's only putting density here. But what is happening if it's putting density here? So that means here the density is either super, super low or it's zero. So that's the worst thing. So what happens if the density is zero? So you have P of X divided by zero. And so that's, infinity blows up, and so not great. And so in order to avoid like a super, super large loss, like what the machine learning system needs to do, if you would be able to train like this forward KL divergence, it would try to do like what's called like a mass covering thing. So we'll try to at least put density everywhere where there's actual data, right? And so this is then you force your kind of approximated density to spread out a little bit, and actually have some diversity and not just kind of live on one. So mode collapse would be basically if you just have like a single delta peak, or you're only focusing on a single part of the true data set. Okay, so here basically, so this would lead to KL, So the nice thing is we don't, exactly, very good point. We're not able to evaluate P of X. But if you think, okay, what do you need to learn the thing to minimize the KL divergence? You only need like the gradient of this thing. So the terms of you expand this expectation, is you have like a expectation of log P. And so this doesn't depend on the phi. Yeah, it's just like some constant, and you don't really need it. And so that's like a nice little property. Yeah, but good point. Okay, so when we say, okay, we want to minimize, and this is exactly what I have here. Basically, when we minimize 4K levers, it's like another way of saying, okay, we are minimizing the negative log likelihood, which is what we normally do in fitting anyways, right? So you just say, okay, I have some kind of model of like which is parameterized, and I just want to move the parameters of the model so that they fit the data, right? And of course, then it's idiotic to ignore data that you have, right? And so it has like this mask covering property. Okay, so let's say let's go then. We want to estimate P of X, and how do we do it? And we're going to discuss two ways to do it. Densities and come up with all these different constructions, right? And so in a way, for example, we've been modeling densities, not even just raw densities, but even conditional densities, like all our lives in during this course, right? So like cross entropy, we had like our family of densities that we modeled, Q of Z given X. We have an expectation value, and then we're asking, okay, what are like the there should be like argmin, because we're not we're maximizing the log probability, but we're minimizing the negative log likelihood. But we have our kind of loss function, and we have our modeling piece, right? So we model Q of phi given Z of X. So why should kind of the modeling Q of X be more difficult, right? It's not obvious why this should be the case. And so, but if you look more closely, it becomes more obvious why it's difficult, because the way that we build this family of densities is by like a fairly kind of not like super pretty trick. So we just took like a density that we know how to evaluate, right? And so those come with parameters, and then we just basically say, okay, we just stick in like a neural network to predict the parameters based on the data, and then okay, you have like some kind of density, which is maybe like a sigmoid, which only like Bernoulli, it only has 0 and 1, or like a categorical, which could be. And so, if you think about it, like there's a strong assumption about the dimensionality of the data. So we think like, okay, the latent code is like a simpler space anyways. It's not so complicated. And so, if you have like a digit of a 5 as an MNIST image, okay, how is the posterior going to look like? Okay, it's not going to be like super crazy, but it's probably going to be centered around 5 or something like this. And so kind of all of these things play a role. And so modeling high, so these are low dimensional densities, right? And so modeling high dimensional densities is a very, very different game. And so, the probability that like our kind of, a textbook density family, like a Gaussian, is going to somehow represent the true data, like the distribution of faces in the world, or the distribution of sentences and all these different things. I mean, that, probability is 0, right? I mean, you can try to optimize it. Okay, which Gaussian is like the least bad in kind of approximating the real data, but it's not going to lead you to anything real, right? And so it's just, very unlikely that these things are going to be distributed in a simple way. So what like exponential to x minus mu squared. So the log density is just x minus mu squared. So you just take like the pixel values against like your predicted pixel value. And so we'll just kind of take the average of all the, you know, if you look at this pixel, so for every digit, it's gonna be kind of distributed, and I mean, we'll have different values. So but you only have like one prediction with your mu, and so it will basically just try to match like the average. What else can I do, right? Okay, so this is basically like a sketch of, you know, why this is doomed to fail. So what is the true, like in the 784 dimension? Better than putting it here, right? And so in that sense, you're optimizing and minimizing the distance between the true data distribution or the Gaussian. But I mean, you know, just because you minimize the thing is you just made it less bad, right? It's not really like a good description of the data. Yeah. No, so this is so imagine this is like the Jeff Hinton saying, okay, so we're plotting one dimension, we're thinking to ourselves, this is 784 dimension. No, no, this is just you look into X. So like in the space of the MNIST digits, right? And so what is one MNIST digit? 28 times 28 pixels. So like you have 784 floating point numbers. So every MNIST digit is like 1 point in a 784 dimensional space, which we represent as a one-dimensional space. Okay, it's not perfect. But then, so in this 780, so you can imagine, okay, like all the ones are somewhat similar. And so it's true, like an autoencoder will try to basically map like this type of structure into like a lower dimensional space, because clearly there's so much space in the 784 dimensions that you don't really need. And so you can kind of represent the same type of clustering also in lower dimensions. Okay, yeah, but so what I meant here is like, okay, like the total data space. Okay, so okay, this is not gonna work. So no, how often? So how often does the density is how often does a specific image occur? So that you're modeling the probability of an image, right? And so an image is represented by 784 numbers. And so if so this x-axis, so whenever you take a point on this x-axis, you're specifying 784 values. And so you're specifying an image, and what you're trying to answer is how likely is this image under the density that generated also the MNIST digits. Okay, any other questions? Okay, so then autoregressive models. And so when we're talking about sequence models, actually that was, I kind of hinted at it at the time, but I didn't make it super explicit. It already was like a, kind of complex model that had a tractable likelihood, but also could represent very complex types of data set. And so, like images, so images are of course like very complex distributed. Right, of course, like sentences are not easy. Like in the space of sentences, I mean, not every kind of sequence of characters is equally likely, right? So you have like certainly some kind of peaks. And so, but somehow ChatGPT, for example, is able to represent this probability density in a kind of convincing way, right? And to the extent that the LMU is hosting like an event about the impact of ChatGPT to, your lives. Okay, so then, but then you can ask ChatGPT, how does ChatGPT itself generate such convincing sentences? So like clearly it's not trying to model everything with the Gaussian. And so if you let ChatGPT answer, and read what the answer is okay, my training process involves predicting the next word in a sentence based on the previous words. And then I'm being evaluated on how well my predictions match the actual text, actual next word. And so this is kind of secretly, like a tractable likelihood model. And so we're gonna kind of formalize this a little bit. Okay, so how can we formalize this? So we can kind of think back to like very basic probability, things. So when we use, for example, like Bayes' theorem, so let's say we have two random numbers, we can always kind of express two random numbers as like the product of like a marginal and like a conditional distribution, right? So you can say, okay, if you want to have like the joint probability, you say, okay, what's the probability to have like 1 point on the x-axis, and then you take, okay, what is the conditional probability to, move in some y direction, right? And so you can say, okay, either it's like p of x given x2 times p of x2, or you can say like the other way around, what like p of x2 given x1 times the marginal probability of x1, right? And so that doesn't really matter. And then if you kind of pull one of these marginals into like a denominator, you get Bayes' theorem, right? Okay, but all these things, like this thing, is very easily extended to many more variables. So you can take, for example, 3 variables, and so you can say, okay, we can use the same thing that we had for the 2 variables. Let's think, okay, we think of x1, x2 as one union, and so we just then use kind of like the first version of this thing, and then we say, okay, it's like the probability of the union given x3 and times the marginal probability of x3. Okay, but now we have like this union, now we split it apart. So that now the union is not a union anymore, but it's like a pair of random numbers. And then we can use again, kind of recursively, this thing in the first line, and we can split up x2 and x1 also into conditional probabilities. And so in the end, what we get is we have here, so here we use, okay, x1, x2 is x1 given, x2 given x1 times x1. But because x1, x2 is conditioned on x3 anyways, you always have to add like the x3 to these things as well. So you get p of x2 given x1, x3 times p of x1 given x3 times p of x3, right? So you can kind of have a high dimensional likelihood on the left, x1, x2, x3. Okay, it's not super high dimensional, 3-dimensional, but you can split it into lower dimensional likelihoods. Okay. So, we have now 2 variable example, like the ordering doesn't really matter. You can use any ordering that you want. You can have, like the fully unconditional marginal to be x3, or you can have it be x2 or x1, and then you can basically choose whatever ordering you want, and you can just split up, the data in any case you want. So this doesn't really necessarily kind of represent like a causal ordering. It doesn't mean that x2 is depending on x1. You can also, have like an inverse ordering. It's just a conditional distribution. So this is just math. It doesn't really say anything about the data. It's just you can split up your density into these conditional densities, any way you like, right? The important thing is that you need to kind of accumulate the right conditioning pieces, right? And so you will see exactly what this structure is. Okay, but before we go there, we can basically say, okay, we can, always choose like a canonical order where kind of the numbers are increasing. So you have like x1, and then you have x2, which is then conditional on x1. You have x3, which is conditional on x2 and x1. So you can always kind of label the dimensions in a way and kind of do this factorization in a way where kind of like the random variable is dependent on all the previous random variables, right? So, and the way to write this usually is, okay, we have like this big product, right? Because we have a lot of product over conditional densities, and like your current variable depends on all the previous variables, right? So xi is conditioned on x smaller than I, right? And so this basically then like this shorthand notation stands for like all these different things. It just becomes tedious to write this down for 784 factors of x, right? But you can kind of imagine what it looks like. So 784 is conditional on 783 and 82 and 81, blah blah blah. Okay, great. So that's great. So we can kind of split up so we started out, okay, how can we represent P of X? Because we want to learn P of X using some variational system Q of X. And so we can now split up our very complicated high dimensional distribution into many little pieces, which are conditional distributions of lower dimensional data, right? So in fact, here, like the X's are one-dimensional data, right? So it's a one-dimensional data distribution. And so that's much easier to handle than a high-dimensional data distribution. Okay, so what is the structure called? So this structure of basically what you're doing is you're modeling, okay, like the distribution of the present, like xi, conditioned on the past, right? And so you remember what ChatGPT was saying, okay, you're trying to model like the probability of the next word, or like the word that you're predicting at the current time step based on all the previous words that you've seen, right? And which include your prompt, what you put into ChatGPT. And so this structure is called like an autoregressive model. Why is it called autoregressive? Because so you're trying to predict like a density. So this is like, yeah. So xi is the present. So you have your words so that you're trying to predict. And what is the context that you're predicting it on? You're predicting it based on the past. So you have xi conditioned on all the previous. Well, so this thing, yeah, so we'll get to this. But I mean, so this is generally kind of doable for any high dimensional data. So we'll get, so for sequences, it's easy to understand why this works. And so we'll get to how to handle other. We'll get to this. Okay, so basically, so this is called autoregressive. Why is it called autoregressive? Because you're predicting something based on yourself, right? So X, you're predicting X based on X, but on like, some slice of X, which like fits in the past, right? So you're, predicting based on yourself. And so this is what's called an autoregressive model. Autoregressive models are used in econometrics and like time series forecasting a lot, even before deep learning. If you're trying to predict, I don't know, like the weather, you have like a time series, so you're trying to predict tomorrow based on, yesterday. And so this is, of course, nothing completely new, but so it's good to kind of be able to place this term. Okay, so then basically what we achieved, okay, we have an autoregressive model, and it breaks up the modeling of the very complex high-dimensional distribution P of X into many factors of one-dimensional distributions, which are conditional. Okay, and so conditional learning low-dimensional conditional distributions should ring a bell, where we have done this before. Okay, so so we actually discussed autoregressive models. I didn't name it at the time in our RNN lecture. So we had, I think, lecture 9 and lecture 10. We had discussed sequence models. And basically, we have two paths to have, to get autoregressive models. And so either you basically have, so you need to somehow have this conditioning P of xi given all the x, before I. And so what RNNs do is they basically embed all of these xi into like one fixed dimensional representation, which we discussed is nice because you can basically have like an infinite stream of data and you have like a fixed memory. And so you're kind of taking all the previous x's and you stick it all, like mash it up into, what you call the memory, right? So you're encoding your past into some fixed dimensional data. But then we also discussed there's like this other direction where we talked about like causal convolutions and so on. And basically, this is just a network architecture where you have like a feed forward thing. You don't have like this recurrent picture. And you basically just feed in the past as an input to the network. And then this is basically like explicitly modeling like this type of conditional distribution without kind of encoding this into like a fixed dimensional representation. The only way to do this is to cut this off at some point. And so there's some kind of implicit assumption that, okay, when you say, okay, what is the probability of the next word given the previous words, you don't really depend on the word that was said like a million time steps ago. So, you're like operating within some kind of context window. Okay, so this is kind of, but both are autoregressive as a property. So both are modeling like conditional distribution based on the past. just that the RNN is encoding the past in like a special way. But sometimes people make this distinction that they call like the right-hand side like an autoregressive model, and then the left-hand side, so that's like a recurrent model, but they both are kind of from a mathematical perspective, like obey this autoregressive property. Okay, so then how do we train an autoregressive model? It's very simple, actually. Okay, you sample some high dimensional X, so some kind of high dimensions, whatever I have here, 20 or something. And then so now you have some high dimensional X, and you order them in some path. So you need to put like some ordering into this, however many dimensions you have. And then because once you have this partial ordering, where one is like next to the other, then you can basically split into like the present and the past, right? Whether or not that corresponds to like a true like timing or something like this doesn't really matter. You can take any kind of 20 objects, you put them into an order, and then once you put them into an order, you can split it into one dimension and like say, okay, this is now the past and this is like present. And so then, okay, you can now randomly pick like a time point. So, okay, where on this axis of, dimensions, you say, okay, this is the thing that I want to predict, or this is like the time where I'm predicting now. And now you just do like classic supervised learning. So what does it mean to do conditional, modeling of, the conditional distribution? What is like the present given the past? It's like a prediction task where you know what you want to predict because you have the data anyways. And you have the past, and so you try to say, okay, I stick the past into a neural network, I predict something, and then I compare with the actual target, what the data is, and this I stick into a loss function. And so this is when we introduce unsupervised learning. We mentioned self-supervised learning. So you're basically generating supervised learning tasks from just data by basically artificially saying, okay, this is now the thing I want to predict, and this is the part of the data that I want to predict it from, right? And so this is what's called self-supervision, and this we know very, very well how to do, and a lot of neural network architecture were designed to do this very well, and so we are kind of confident that we can solve this problem. Okay, so once we have this, any questions? Okay, so once we have this, we can basically do both of these pieces. Yeah. Yeah, so you would probably, normally, let's imagine this is like 1,000 objects. And so either you have like a neural network that can handle like a variable number of objects, and like a recurrent neural network would be like an example, right? Because in a recurrent neural network, you can stick in as many things into memory as you want, right? And in principle, like the memory is supposed to like remember like all the relevant pieces. Or you have a neural network architecture that cannot handle like an infinite amount of inputs or like a variable amount of inputs. And then you have a neural network that can maybe like handle like a maximum number. And so then you're saying, okay, my conditional distribution, what is the present given the past, only really depends on the last 100 like inputs. It doesn't really depend on the. Yeah, so it's a kind of like a Markov. Well, so Markov properties, you only depend on the last step. Right. So in the Markov property, you only depend on like the last step, and you try to predict the same. If you're depending on like a context window, then it's not exactly Markov. Yeah. So if you call this thing your state, then it becomes exactly. Okay. So now we can basically do both of these things that are related to P of X, right? So we can evaluate the likelihood. So why can we evaluate the likelihood? Because we, from our supervised learning, we do like the standard trick of, we have like our simple distribution, we predict the parameters of the simple distribution. So we can evaluate this density. And then, because we can evaluate all of these conditional densities, also means we can evaluate the global densities by, following this factorization. And we can sample from this density by sampling step by step. So we start with the thing that is, x1, there's no x0, so we just sample x1 from the marginal thing. And then once we have x1, we stick it into our conditional model. P of x2 given x1, we sample x2. Once we have x2, we stick it into our conditional model of x3 given x1 and x2 and so on. And so we can sample kind of step by step. And by sampling and concatenating, you're basically sampling this high dimensional distribution, in a very, very straightforward way. Okay, so the advantage here is basically that because we split up everything into these tiny little small supervised problems, we can use our kind of wrapping density trick. So we have still our thing where we kind of wrap out and take some kind of known distribution, and we're just using the neural network. So the x here is like the past, right? So we stick in the past, and so this is now the present, and it's like a simple supervised learning problem. And so we actually discussed exactly this procedure in detail when we discussed how we do like language modeling, right? So back then we didn't really kind of make a big point about that this is like a generative model and we're doing unsupervised learning, but like effectively this is what we've done. And so the simple density in that case was like a categorical distribution, where this neural network is just predicting like all the probabilities of which word is next, right? And so it's not like a super tiny distribution. So for example, like in vocabulary like French or something, like we had a like mini French language, right, where we had like 5 words or something. But then like the global language, of course, like maybe thousands of words or tens of thousands of words. But like if you compare to the distribution of like sentences, that's like incredibly high dimensional, right? So compared to that, just predicting the next word is like a tiny problem. Okay, so in order to do this, so this is now your question. So we can basically do this recurrent data fitting and generative modeling also for things that are not like naturally a sequence, because we just we take whatever dimensionality of data we have and we just put some ordering in, and then we just predict in whatever order we want. And so here's like an example for images, right? So we can just say, okay, we just label the pixels 1, 2, 3, 4, 5, and then we go to the next line, 6, 7, 8, 9, 10, blah, blah. And so then you're saying, okay, you have your view of the past, right? And so now you can kind of say, okay, you can decide what is, so in principle, you should depend on the full past, but then, okay, you can say, okay, I'm truncating the past a little bit. And then I take whatever fraction of the past I want in order to predict the next pixel value, right? And so we go from next word prediction to next pixel prediction. You can imagine how we're generating an image. We're generating an image by starting at the left-hand most pixel, like upper left-hand corner. You predict the pixel, 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 and then you just raster scan, all the way through. And it's basically like, generating like a sentence in pixel land. And so what you see here is basically, okay, what kind of value? So what is the vocabulary of doing this type of prediction? So you have like 8-bit values from 0 to 256 values from 0 to 255. And so for every pixel, you get like an intensity value. Is it bright or is it not so bright? Yeah.
Yeah, but when you put in ordering, like I think some of these solutions have very a lot.
Yeah. Yeah. So I mean, when I said the ordering is independent, so that is just like the mathematical factorization works in any ordering. So it's true that like the context window. So here you basically take like the surrounding as like your conditioning thing, and then you're saying, okay, it doesn't really depend on like the things beyond this, but you're only like all this gray stuff is the past. So in principle, you could depend on all these things, but then you choose to only depend on this part of the past. And so that's just like a design choice that you can do. Of course, if you kind of do, okay, based on the upper left-hand pixel, I want to predict a lower right-hand pixel. I mean, that's just like a much more difficult prediction task. And so this is just, okay, how easy is the supervised learning thing? So, and supervised learning is always easy when things are highly correlated, right? And so, of course, like the pixel next to me and the current pixel, they're highly correlated. This is bright, it's, some likely that it's also bright. So whether or not like there's a good correlation between the upper left-hand corner and lower right-hand corner, probably not. And then you just chose like a very difficult small supervised learning task. Okay, so this is kind of this thing in action. So this is from Sarah Forest's slide. So you can see, okay, so you started predicting this thing. So you're writing in an MNIST image. And so where are you? So you're currently, the cursor is here. And so you're saying, okay, what is the next pixel going to be? So the next pixel is kind of to the right of it, right? And so you can see kind of the distribution of predicted intensities in the histogram. So it's predicting low intensities with high probability and high intensities with low probability, right? So it's very high, a high probability that this is going to be like a white pixel or like a light gray or something. It's not going to be a black pixel. Okay, so you continue. So now you have like the next thing. So here you see, okay, it's already starting to shift. So here it's like much more uniform. Right, so here it's saying, okay, the next pixel, which is here to the right, okay, maybe it's, black or white, kind of 50-50, right? And so as you get closer to, where like also, the digit is actually located, as you kind of start like, see that the distribution starts to flip, right? And so you go from predominantly it's going to be white to predominantly it's going to be high intensity or black. Right, and so once you're like in the middle of this digit, it's really predicting, okay, it needs to be black. Okay, and so you can see, but you can kind of imagine how it's writing this little digit. It just goes kind of line by line. Okay, so and this answers the question. You just need to put some ordering that generates highly correlated, supervised learning tasks. Okay, so then there are more complex examples. So this is kind of like the easiest way to do kind of autoregressive models, right? So by doing like this next X prediction, where X is maybe like a word or like a pixel intensity value and so on. But we can do something more complicated. And so one of the things that people do is to combine the autoencoder structure or like a sequence to sequence mapping with an autoregressive property. And so this is called masked autoencoders. And so we can see, so I'll not go into detail here, and it's kind of more just for you to look up in the literature if you like. And so what is an autoencoder at a super high level? At a super high level, an autoencoder just maps like some kind of value X to some kind of value Y, where X and Y have the same dimensionality. Like a typical autoencoder has like some kind of bottleneck in between, but okay, it's not really important for this type of discussion. Okay, so what can we do? And so basically, maybe we can interpret Y, as a kind of prediction. What is the probability, like the autoregressive probability that the value is this probability given like the previous path, right? The problem with this idea is that, of course, like in a typical autoencoder, I mean, nobody taught it about autoregressive properties at all. So every connection is every position is connected to every other positions in the data set, right? So you don't have Q of xi given Q of x smaller than I. You have Q of xi given all of x anyways, including Q of xi given xi. So it's kind of like reducing this to like a trivial like identity mapping, right? So it's not it's kind of like a trivial task, and it doesn't really have an autoregressive property. But you can imagine, okay, maybe so the reason why this is because you can basically trace to any Y position, you can go to any X position by walking through the autoencoder through like the weights that you have in your neural network, right? Which are kind of edges in your neural network graph. Okay, but a masked autoencoder basically changes this by kind of very precisely cutting specific connections in the autoencoder so that it effectively has an autoregressive kind of connection schema, where basically you're saying, okay, I want my outputs to predict, to represent, like all these conditional factors that I want. So if I had like when I had a three-dimensional data set, I had three kind of conditioned, like in my factorization, I had three terms, right? So I had one term that is conditional on two, like the previous two things. I had one term that is only conditional on one term, and then one like super marginal term. And so you have this construction where, okay, if you have n-dimensional data, you have n little kind of conditional probabilities you want to model. So this n-to-n mapping that an autoencoder has is already pretty good. And but the thing that we need to ensure is that okay, whatever like is the output of you know the thing that is modeling x1. So in this case, only depends on x2 and x3. So here you notice they didn't bother to like put this canonical ordering, and so we know we can just put in any ordering. So they wanted to model x1 given x2 and x3. And so like absolutely not, like can it, should this node be connected to x1, right? And so it's a little bit difficult to understand from this picture because basically the kind of the gray shades of gray represent which connections are which, but you can kind of trace that you know the x1 is not connected to the node or is only connected to node 2 and 3 and not connected to node 1, right? And so the rule is here basically all the output nodes that are labeled K can only connect to output nodes that are labeled with some number m smaller than K. So that you can see the 3 is connected to 1, 2, and 1. The 1 is not connected. So the output node 1 is not connected to anything because like it models like a completely conditional density P of x2, right? So you see basically, okay, here this term doesn't have any conditioning pieces, so clearly it cannot depend on the data at all. So it has zero connections. It's kind of like a free floating piece. And so this cannot connect to any of these because the thing that is labeled with is needs to be smaller than whatever numbers these nodes are labeled with. Here it's already better, so the 2 can connect to the nodes that are labeled 1, right? And then the internal nodes, they can connect to either nodes that have the same kind of label attached to them or smaller. So the 1 can attach itself to the 1, and so you can see, okay, this thing is basically connected to x2, right? So you can go, okay, this is modeling x3 given x2, and so you, with this kind of path, you get to x2. Right? Yeah. Sorry? No, so this is like an external, so this cutting of certain connections. So like a normal autoencoder is on the left where you have all connections, and the masked autoencoder is on the right. And so you generate these masks yourself as externally. And so the neural network doesn't know, but you enforce this autoregressive property on the connections by only allowing connections that like together yield like this autoregressive picture. Sorry? Yeah. Yeah, so then that gets I mean it's basically, I mean what are you doing? So you're I mean you're modeling some kind of marginal density, and so your marginal density, let's say it's like some pixel value, you need to model like some kind of distribution, but the distribution is just not kind of conditioned on the input x, and so it's like just a trainable parameter. So it's just like a free floating parameter. You can basically learn, okay, what should this super marginal thing you know, be initialized with, or you initialize it, then you train it. Okay, so basically by some like very careful you know analysis of which connections are which, you basically allow only autoregressive connections, and by this you can basically train like an autoencoder. And what's nice is you get all the factors in one go. Like you just run the network, you get all the factors in one go, and so that's really nice. Okay, so this specific setup is called like a masked autoencoder for density estimation, or MADE. Okay, so then you can kind of generalize even from an autoencoder. You can say, okay, like this doesn't even look like an autoencoder anyways. It doesn't really have like a bottleneck and so on. It's just basically like a map from 3 dimensions to 3 dimensions with some kind of communication in between. And so really any type of architecture that maps n dimensions to n dimensions is a useful thing. As long as it has like this autoregressive property kind of built in. So this kind of brings us back to ChatGPT, where basically, okay, we're saying, okay, transformer at the highest level is just a sequence to sequence mapping. So you map n things to n things. So that's great. So because we know we have n inputs, we have n condition like autoregressive pieces. And so that now there needs to be a little bit of crosstalk, right? But we need to ensure that the crosstalk doesn't break this autoregressive property. And so this is basically ensured by this attention mass becomes diagonal or like lower triangular in the sense that so it was always a question, okay, can I pay attention to? And so if you're at position 3, you can only pay attention to position 2 and 1, right? You cannot pay attention to position 4. And so by having like a specific like math attention, then you can basically enforce this autoregressive property in a very, very natural way. And so this is called like causal attention. And this produces this autoregressive property very easily. And so this is essentially what ChatGPT has, like in the decoding piece of it basically gets your input sentence. So maybe you put in 3 words, right? So in your ChatGPT prompt, right? So you say, hello ChatGPT, whatever, shout. And then so the next word is now going to be like the 4th word and the 5th word that the ChatGPT needs to generate. And so the 4th word can only kind of look at your prompt, which was 3 words. And so we'll have like this causal attention, it can only pay attention to these things. And then the 4th word, it will generate, like a model of what the next word should be. And then once this word is generated, the next word can, incorporate that information. So this is, how you generate very long sentences by going step by step. And so the width of the sequence to sequence, basically the context window of what ChatGPT has, and how much does it kind of keep in memory. Okay, so but the point is that any sequence to sequence model will work as long as you're ensuring that somehow, like within the connections, there are no kind of cheating paths where you can look into the future or something like this. Okay, so this gives us a summary. So autoregressive models are a great way to break up, the difficult task of having high dimensional densities into, which is unsupervised learning, into many smaller supervised learning things. And so it's like an example of self-supervision, where basically the data, generates the data. I mean, you're just splitting the data that you have into what you call a label and what you call like the conditioning thing. And you try to predict, the data from itself, but from a different part of itself. Okay, great. So this is one way to do high dimensional densities. And so the other one is what's called normalizing flows. And so this is also something that then came out 2016 or something like this. So a very kind of conceptually nice way to model densities. And so let's kind of go step by step. So we're basically like an alternative to autoregressive models, and we can marry like standard probability theory that we know and love from statistics with the thing that deep learning is very good at. Is like super deep composition of functions, right? And so how do we do this? Basically, we can say let's assume we have a known distribution P of X, and somebody gives you some kind of function, so you can sample values of P of X. You can evaluate the density P of X, and let's say somebody gives you a function that maps X to Y. And so now what is the distribution of Y, right? And so the distribution of X, there's a deterministic mapping from X to Y. And so because the X is random, Y is also going to be random. And so depending on the details of how X is distributed and what the details of f of X are, Y is going to be distributed in some way, clearly, right? And so the question is like, how is it distributed? And so the way it is distributed is, you can write it down in a fairly straightforward way. So, what is the probability density of observing one Y? Basically, you want to scan over all possible X's and pick up all the pieces, all the X's which produce Y, right? And then you weight them with, what is the probability to get that X in the first place, right? So you're just kind of going through the space, vacuuming up all these different X values that produce Y, and then you do like a weighted average, basically of, the probabilities of those X values that produced Y. Okay, great. So this is kind of a formula that is, like it's a scary integral. But actually turns out for like a certain class of f of x, it becomes very simple. How does it first look for like complicated things? So if you have like complicated things, so really like this integral becomes complicated if there are like multiple x's that produce the same y, right? So that if you have, for example, x squared, right? So if I say, okay, what is the probability to get like y equals 4? Clearly, like x equals 2 and x equals -2 contribute to the probability of observing like y equals 4, right? And so you can kind of plot, okay, let's say I have my Gaussian distribution of x, and then whatever my Gaussian distribution for every x, I map it on my parabola. And so if I take the histogram in this direction, this is basically what is giving me the distribution of x squared, right? And so if you remember your statistics class, you know that this is the chi-square distribution. So it's the square of a Gaussian random number is the chi-square distribution. Okay, so it happens to have a name, but I mean, it's not obvious that you can solve this integral like in an easy way, especially if f of x, I mean, you know, maybe it's not like x squared, but it's like super wiggly and, you know, like it picks up like for a lot of different x values, produce the same y value. So this can become tricky very, very quickly. But we can look at a simpler case where we have like one-to-one mappings, right? So where there's always only one point of x that produces the y, where you have basically like an invertible function. So if I give you a y, you can you know, uniquely determine which x that produce this y, and then you just go and look, okay, how likely was this x to begin with, and that is your density up to one factor, which is very, very important. And so if you go through this thing, so let's say you have like a bijective mapping, you can go through like the rules of delta functions and so on, and basically what you end up with is this function at the bottom, where p of y is basically p of x, but it's scaled by the derivative of this mapping from x to y. And so we'll kind of discuss this in detail like in a second, but this is maybe you've seen this before. So basically like the probability of some new value is, okay, you need to map the new value to the old value that produced it. And so you go like the inverse, and you know, this probability you know anyway, so you know what p of x was, but you need to scale this when you're dealing with probability densities by the derivatives. And why is that the case? And so this is just kind of rewriting it or deriving it a different way. So you can basically say, okay, the total probability needs to be preserved, right? So I can't lose probability by just doing like this mapping. So p of y times dy, which is like the probability, because the p's are just probability densities, right? So actual probabilities are always only defined when integrating over an infinitesimal piece. And so this needs to be preserved. And so you can say, okay, you do like the physicist's version of dealing with differentials, and you divide by d of y, and then you have dx divided by dy, which you say is 1 over dy divided by dx. So there's like mathematicians will kill you, but it all works out basically. And so you have the same kind of structure that p of y is 1 over the derivative times p of the inverse of y. Okay, so that's like math. It's very easy to visualize why this needs to be the case. And so you can kind of imagine, so if you have like a sigmoid, so you have like a Gaussian number, so instead of like a square, like a parabola, you now have like a sigmoid, which is a bijection. So for every sigmoid, you can uniquely map, okay, which x value corresponded to this. But you can see, okay, like here, like the sigmoid, you know, a lot of these x values can basically map to the same y, right? Because the sigmoid output doesn't really change. And if you're saying, okay, like basically x equals 5 and x equals 10, they all produce the same y value. So they're kind of relevant to determining what p of y should be. And so if you have like a flat function where the derivative is small, you know, you're basically inflating the probability of the output, because you're collecting all of these x values, you know, along the way, right? And so if you have, so the probability gets larger if the derivative of the function is low, right? And so that means, okay, you want to kind of divide by the probability, by the derivative, right? So that if the derivative is low, you're scaling up in a large factor, right? Okay, so low derivative, large increase in density, and that's why you have like this inverse mapping. So we can also imagine like the look in a different piece. Like here you can see, okay, the like the probability of for like intermediate y values is depleted, right? So even though for x, it's the peak of the density is actually at x equals 0. But if you look at y, it's not the peak, it's actually like the inverse of the peak, right? And so it's a throw or something. And why is that the case? Because even if you change like x a little bit, suddenly the y value is like vastly different. And so you stretch out the probability space, and so that just kind of really thins out the probability in the y space, right? So if you have a very high derivative, you have a large decrease in the density, and so that matches also this formula that we have. So 1 over the derivative, and so this is roughly how you. And so this turned to what used to be a peak. So the piece on the right, so the p of inverse of y, that is a large value, but it gets basically killed by this very large derivative term as well. Okay, so this is basically this derivative factor accounts for, okay, how much does the function stretch the space, or how much does it compress the space? So here it stretches like a very small area in x into like a very large interval in y. And here, basically, you compress a very large interval in x into a very small interval of y, right? And so this is what the derivative basically captures. So in higher dimensions, this kind of looks the same. So you can basically generalize, from like this one-dimensional thing into high-dimensional things. So, and if you remember your multivariate calculus class from, I don't know, maybe the second semester or something, you'll know that the volume element of y is basically scaled by the determinant of the Jacobian, or the absolute value of the determinant of the Jacobian. And so it's the same thing. The Jacobian basically captures, okay, your kind of volume epiped or something like this. I mean, how does it get stretched and squished and, in high dimensions? And so this is basically, okay, you go from the dx volume into the dy volume. And so the function, the details of the function stretch the space a little bit. And this is basically how you combine, your volume elements. Okay, so then we're already almost done, right? So what have we achieved? So we can start from a very simple density, right? And let's say somebody gives you like an invertible function, right? I realize this is not an invertible function, so it's not a great example, right? So like ignore like this piece here. But I mean, in principle, like, okay, at least this piece is invertible. So you have a great thing, you have like an invertible function, somebody hands you an invertible function, and then you can turn like a very simple distribution that you know and can control and all these things into a very complex distribution, which is exactly what we want to do with the data, right? And so that's excellent. And so not only can we kind of sample, so how do we sample from this? So it's very easy to sample from y, because we can sample from x, and then we just stick it through our f of x and to get like a sample of y, right? So it's a very simple operation. But we can also evaluate the density by going backwards. We take the y, we map it through our inverse function to x, and in the x space, because we know it's like a very simple density, we know how to evaluate this density. And so we can, as long as we can compute all of these derivatives, we can evaluate p of y by going basically to the x space, right? And so that's great. So exactly what we want. We want to have like a complex density to model the data, but also one that we want to be able to evaluate. Okay, so then this gives us kind of a very powerful tool. So that's exactly what I just described. So the generation part is, okay, you sample from the simple distribution p of x, you apply f of x, and so effectively what it does is to sample from this marginal density p of y, and then the evaluation is also easy. You take your y value. So if I say, okay, how likely it was this value of y, you go to the inverse, you evaluate the derivatives, and then you apply your change of variable formula, and then you have your density value. So, okay, that's great. So now, what's great is that we can not only do this once, but we can compose. So, whenever you have like some kind of density, you can stick it through some kind of bijection, and then it becomes more complicated because it squishes and stretches the space even more. And so you can say, okay, you can go from a simple distribution to a slightly more complicated distribution. And now if you have like another bijection, you can make the complicated distribution even more complicated and even more complicated, even more complicated. And the only thing is, you can, if there are like bijections, you can always go inverse and inverse and inverse. You can traverse this sequence of densities without any problems. If you accumulate all the determinant values, you basically can evaluate the density of this very complicated distribution by going backwards, picking up all the determinant Jacobians and adding them together, which gives you like the global Jacobian of the composition of the transform. So the Jacobian of both of f followed by g is just the product. So this is the chain rule, right? So of composed functions is the outer function, the derivative of the outer function times the derivative of the inner function. And so you just, and in the log space, this is just addition. And so you just add like all these determinant log, Jacobian terms, and then you go all the way to the simple distribution. This is where you know how to evaluate the thing because you designed what this distribution is in the first place. Okay, great. So you go from very simple to very complex, but keep the ability to evaluate the density by having bijections. Okay, great. Okay, so how can we learn invertible mapping? So all of these examples are also not invertible, so I apologize for that. But basically, okay, we're looking for functions, right? Okay, we were looking for invertible functions, but we don't know which function we need in order to stretch the space so that the Gaussian becomes like the distribution of faces. So we want to look for it. And so this is looking for functions is what deep learning is very, very good at. And so we'll try to basically use neural networks to find good bijections in order to match the distribution that we need, right? And so we don't know. So there's, let's say, so this is like the unsupervised learning test. We have some data, right? And so we assume our simple distribution. Now the task is, okay, can you find a bijection so that the density is at the right places where you want it? Okay, so then, this is what we call like a normalizing flow. So we have like a stack of learnable functions, and we just basically, have like this stack from simple distribution, slightly more complicated, blah, 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 blah. And then we can go backwards. And it's all about finding, okay, what are the right bijections in order to generate the density that you want, which is represented by the training samples. Okay. So, there are two problems. So this sounds maybe too good to be true. So there are, of course, two kind of tricky problems. So we need to find like an expressive way, like a powerful way to, define invertible functions. So of course, like if these functions are too simple, right? So then you're not really changing the simple distribution to anything complicated. You need like a lot of wiggles and like all of these things in order to really like meaningfully change the density. But at the same time, it needs to be invertible. And so it's very easy to come up with invertible functions that are simple, like a linear function is invertible. But it's complicated, very complicated to find like a family of invertible functions that is, has complex enough members in this family to meaningfully change the density. And so you want to have like an expressive way to have invertible functions, and like standard neural networks are not invertible, right? So there's no reason why they should be invertible, and so of course they're not. And like universal functional approximation, tells you that it's not invertible because of course neural networks are also able to like approximate the non-invertible functions, and so clearly you need to do something. And then there's also a problem if you have high dimensional data. The Jacobian is, it's the square matrix of data times input dimension times output dimension. And so like for high dimensional data, this is even going to be worse. It's squares of high dimensions. And so you need to have like a tractable way to evaluate the Jacobian. Right, so there are a number of solutions available. I'll quickly go through one example. So there's like masked autoregressive flows, which are similar to like the masked autoencoders, and then we have inverse autoregressive flows and all these different things. And so I'll focus on real NVP flows, and so this stands for real valued non-volume preserving flows. Also, why are they called normalizing flows? The reason they're called normalizing flows is because if you go backwards, so let's say you want to start like evaluating the density, you go backwards, and as you're going backwards through all of these different densities, it becomes more and more like Gaussian looking, and so more and more like a normal distribution. So that's why it's normalizing, which is funny because it's like if you use it as a generative model, you usually think of the other direction, and so it's actually like a complexifying flow. But like if you're evaluating, this is the direction where it becomes normalizing. Okay. So how can we do our real MVP flow? So one strategy to get expressive invertible functions is kind of like an interesting construction, which makes sense only once you kind of think about it. So basically, what you can do is you can squish and stretch only like 1/2 of the coordinates based on like a function that is defined on based on the other half of the coordinates. And so basically, okay, if you're saying, okay, I split my data into 2 halves, and now I want to change, like I want to do a bijection. Of course, the identity is a bijection, so you can always kind of the 1/2, like the green boxes, they just stay the same. That's a perfectly fine bijection. And now you want to basically say, okay, for the other half, this is what I change, and I change it by combining, the green and the blue box into some kind of new representation. But then you alternate. And so now like you change 1/2 and you keep the other fixed. And now for the next step, for the next bijection, you flip, right? And so you kind of do this game a little bit. And so what does this bijection look like? So the 1/2 stays the same. So from 1 to D, this is just like a constant, like identity mapping. And then the second half is a function of the first half and the second half. And so this is what you have here. I don't know why I don't see the mouse, but so you have a function of the first half and the second half. And so the second half is basically acting as a conditioner for just like the transformation of the second half of coordinate. Okay, so what does this look like? Or how can we make this invertible? And so there's a very, very neat trick. You can say, okay, let's say you have like this type of construction, right? So you have like the original data, which you multiply by like a scaling factor, which is like exponential times some function of x, plus you have like this t function of the conditioning half. So you have, so you basically have like your original data, which you scale and shift, right? And then you get some new values y. And so now the question is, like, what's the inverse? If I ask you to kind of rewrite this function in order to get xd plus 1 through d from y, how would you, using your elementary math skills, kind of invert this? Can you write it down? Yeah.
You can just get one part stays the same, and then you can find it.
So I mean, so you want to have like the x d plus 1 blah blah as a function of the y d plus 1 blah blah. So how do I get this? Okay, it's not very complicated. So you do y minus t, right? And then you divide by the exponential. And so what is like 1 over exponential of a number? That's the exponential of the negative, right? So a 1 over a to the x is 1 a to the minus x, right? And so that's basically it. And so you can notice a very, very interesting property now. So you can, so I didn't really need to tell you what these functions s and t were, right? And so you can invert this function without inverting s and t. So there's a potentially very complicated mapping s and t, right? That is kind of in this exponential piece and in this like shift piece, right? But the inverse, if I want to compute the inverse, I don't need to know what the inverse of t or the inverse of s is, right? So that's great. So like these pieces can be arbitrary functions which don't need to be invertible, right? And so we know what like a good family of functions is that we cannot control to be invertible, neural networks, right? And so you can have like a very complex, so like depending on how complex S and T is, like an arbitrarily complex transformation, but which you can invert. And so that's great. And so, okay, we have an invertible setup. And so, as I said, the no restrictions of S and T as functions. They can be any type of function, and we will just assume that they're going to be neural networks, which we know are able to express very complicated functions, and they don't need to be invertible. Great. Okay, so then how do we do this? Basically, okay, we will basically say S and T are just neural networks. So we just stick X, so like this conditioning half into a neural network, like into one neural network to like compute the scaling piece. We stick it into a different neural network to compute this like shift piece, and then we have our bijection. And then for the next iteration, we just switch like which half are we transforming, which half are we not transforming. And so that's great. So we managed to like define like a family of invertible functions using neural networks without requiring that the neural networks themselves are invertible. So that's excellent. So that was like one problem solved with normalizing flows. And then the second problem with normalizing flows is also easily solved because of this a funky structure of like this coupling layer. The Jacobian, I mean, very, very structured, and remember, you only need the determinant of the Jacobian. So the determinant of the Jacobian is like the product of the diagonals, like minus those diagonals and so on. But you can notice there's like this big block of zeros. And so if you go like these inverse diagonals, they're all zero, right? And so like this, so you can go through the math, not super, I mean, okay, you have to do it, but I mean, you can kind of imagine that this is a tractable Jacobian. You can actually compute the Jacobian by just evaluating this neural network S, and then you're done. And you needed to evaluate this neural network anyways, because you had to do the bijection. And so it's a very efficient way. So you have two neural networks, you implemented the bijection, you immediately get what the Jacobian is, and then you're done. You don't need to invert like some crazy n times n dimensional matrix where n is maybe like 1,000 dimensional. And so we solve both problems. We have like a tractable Jacobian, and we have like a family, like a learnable family of bijections. And so this is then how we get. So this is like a normal distribution, and what we want to generate is the famous half-moon data set that I think I also had in the exercises. And so we'll see kind of how this arrives at a very complex distribution, at least in 2 dimensions, by squishing and stretching just two, like one dimension and then the other dimension, then the one dimension again. So you're alternating bijecting one dimension and then and keeping the other fixed. And so let's see what this looks like. So you can see here. Okay, great. So you go from a very simple distribution, which is a Gaussian, into a very complex looking distribution, which is like this half-moon data set, right? And so you can, imagine if you were to try to do it using like this standard way of, like doing the average, like the average of this is just 0, like in the half-moon data set. And so if you were just to predict like the average data, you would just collapse into a single point. And so here you have a very nice kind of description of the distribution. And so you can see, okay, every time it shifts like this upper, the y dimension and the x dimension, it alternates. And so this is kind of a representation of this real MVP flow. Okay, so this is a 2-dimensional data set, not horribly complicated, but you can already see kind of what it's doing. But then like for higher dimensions, more difficult to see. So here like some other examples on having the density. You can do like very complicated densities, these checkerboards. So these are like standard benchmarks in machine learning on density estimation, complex densities like these, like circle of Gaussians and so on. And so now we go to very high dimensional data. So this is images. So you can see, you can also generate realistic looking images, maybe not so realistic as GANs. So this is this trade-off between having like a tractable likelihood model versus just sampling, but it's very high dimensional. So you can imagine, so this is like maybe whatever 500 times 500 pixels times 3 channels, because you have like a RGB as well. And so that's great. So this is kind of all like machine learning. And here I'll finish with this example from Lattice QCD, which is basically, okay, understanding the structure of the proton and, quantum chromodynamics and so on. And so it really involves kind of estimating a density. And, where in the flow, in the bijections, you also need to encode a lot of symmetries, which are, similar to like gauge symmetries in particle physics, and so this is very complicated, but by just describing a suitable family of bijections, we can do this. And so we actually have a workshop in 3 weeks that we're co-organizing, where a lot of these normalizing flow things are going to be discussed. Okay, so great. So then that was my summary. So normalizing flows model the data density as a result of a large series of bijections, and like the composition of bijections, they produce like a tractable likelihood model. Very attractive conceptually. In the end, it turns out it's not super easy to, I mean, already the real MVP, it's already expressive, but I mean, to really get the full expressivity of, GANs and so on, it's just difficult. And so, if you try it, it's gonna work nice for a lot of data sets, but, if you try to do images, it's gonna be a little bit more complicated. Okay, thanks a lot. Any questions? If not, the exercise, you'll train the normalizing flow. All right. Why on Zoom?